Hello, my name is Aaron Summerall, and this is my Physics 2212 Lab 4 Circuits Introduction. Description/purpose. Predict the behavior of the circuits containing resistors in series and parallel. Use multimeters to measure the actual values of the conventional current and potential differences in the circuit. Examine how behavior of the ohmic resistors and capacitors. Fundamental ideas. Conservation of energy and charge. Kirchhoff's circuit law, the node and loop rule. Steady-state circuits, Ohm's law, resistors and capacitors in series and in parallel, capacitance, time dependence in resistor circuits, RC circuits. The results, the node and loop rule were satisfied, and RC is time dependent. Experiment and observations. Part 1. Two batteries at 1.5 volts, two resistors, one at 47 ohms and the other at 100 ohms, and two ammeters. Prediction. The I1 is going to equal the I2, which is the node rule. The resistance equals 47 ohms plus 100 ohms, which equals a total of 147 ohms. And the current is going to be equal to 0.02 amps, and when it's backwards, it's just going to be negative 0.02 amps. Replacing one of the ammeters with a voltmeter. The current's going to be 0. The voltage is equal to 3 as read on the voltmeter. This is because it is an open circuit and there is no current, and the potential difference across the opening equals that across the power source. Closed circuit and measuring potential difference. So when measuring from B to C, it was 3 volts. From C to B, it was 0. From D to C, it was negative 0.96 volts. From E to D, it was 0. From F to E, it was negative 2.04 volts. And then from the rest of them, G to F, H to G, and A to H, it was all equal to 0. And this does follow the loop rule, so it's going to be the round trip theorem, and it's going to be 3 volts minus 0.96 minus 2.04, which is going to equal to 0 volts. The current's going to be equal to 0.02 amps. This is because the voltmeter has a very high resistance, so nearly no current flows through it. This leaves the path of the current unaltered. This is going to be a graph of the potential differences, and as you can see at the beginning from A to B, it goes up to 3 volts, and then once it crosses the wire, it remains constant. But as soon as it gets to the resistors, there's a decline, and it'll go all the way down to 0, and this satisfies the loop rule, which is the round trip of the delta V is going to be equal to 0. The ammeter in parallel with a 100 ohm resistor. The current reading of the ammeter rises to 0.06 amps. This is because there's less current because less current comes into contact with the 100 ohm resistor since it splits at the node. When calculating the resistor, it comes out for the 47 resistor, it comes out to 48, and then for the 100 ohm resistor, it comes out to 102 ohms, and the resistor of the wire is equal to 0, and the resistance of the ammeter is equal to 0. The calculations are higher than expected. This is because of the low precision of the ammeter. Notes. The light bulb lights up immediately and then dims quickly. The capacitor is charged when the bulb is out. Removing the battery causes the light bulb to light up. The capacitor is discharging. So the time of the capacitor charge is equal to, for the 10 ohm, it is 8.2 seconds. For the 20 ohm, it is 19.7 seconds. The time capacitor discharge for the 10 ohm is 9.8 seconds, and the 20 ohm is 20.3 seconds. At different time intervals, we measured the voltage as the capacitor was discharging. When compiling all this data and then making it linear, we were able to obtain this equation and solve for the RC experimental, which is equal to 5.828 seconds, the RC estimated, which is equal to 6 seconds, and the accuracy is 97.12%. What if questions? What if you used an actual ammeter instead of the ideal simulated ammeter? The current reading would be lower because of the resistance in the ammeter. Next, what if you used a real battery to charge a real capacitor with no resistor in the circuit? The capacitor the capacitor will take more time to charge and will not charge instantly. Thank you.